Welcome to Ready to Derive. In this video, we continue our study of differential equations by exploring the power of slope fields to make visible the behavior of their solutions. We learn how to sketch slope fields by hand and how to sketch solution curves through a specified point within the slope field. As always, there's lots of practice and pretty visuals along the way, so let's get started. So let's dive right in to find out what a slope field is. A slope, aka directional field, is a visual representation of a first-order differential equation. And what is that? That is a differential equation in which only the first derivative appears, and that first derivative has to be expressed as a function of the two variables involved. It could be just one of them, but it can't be, so it could be x and or y, but not any more variables than that. So here's a slope field for the differential equation dy by dx equals y minus x. And this is a magnificent graph that's produced by Desmos slope field generator. Before we sort of get into understanding how this is helpful, let's look at how it's created first. So it is a graph of all the values of dy by dx for every point on the coordinate graph. So let's take a look. How about dy by dx at 1, 3? Let's see if we just use this formula. So this says take the y coordinate and subtract the x coordinate, and the answer is 2. And how does that show up on the graph? Well, if we go to the point 1, 3, we see a little line segment that does indeed look like it has a slope of 2. Let's try another one, dy by dx at 1, 1. So let's put it into the formula. Y is 1 minus its x coordinate. That should give 0. And if we go to 1, 1, we see a horizontal little line segment there. That's a tangent line to the mysterious graph that doesn't exist yet. But that tells us what the slope is of the function at that point. And let's do one more for practice. Let's do 1, -1. So the y coordinate is -1. We have to subtract its x coordinate. We get -2. And if we go to 1, -1, so right here, that dy by dx looks about -2, and that would be the slope of the solution curve that passes through that point. So why are slope fields helpful? Well, they reveal the behavior of various families of solutions to a differential equation. And this is particularly useful for differential equations that can't actually be solved explicitly, but we can still understand the behavior of the functions they describe. So let's call up the one from the slide before. Dy by dx equals y minus x, and this is its slope field. And we learned how to actually, create this slope field. But now we want to look at a different skill, which is to sketch the solution curve through a given point. So we're going to look at the point -1, 1. Now, we know from before that dy by dx is y minus x. For -1, 1, dy by dx is 1 minus -1. In this case, it's 2. So if we go to -1, 1, we see there's a little tangent line that looks like it has a slope of 2. And how does that help us? Well, that actually tells us the exact slope of the function at that point, -1, 1. We know that the function that we want a curve to pass through -1, 1, and we know that it has a slope of 2. Now, to create the rest of that sketch, so we know it's passing through here with a slope of 2, I want you to think of this as maybe a map of currents in a river. And wherever you drop an object, like a twig, into the river, it's going to follow the path that's prescribed. So if we drop something in at -1, 1, you can get the sense that it has to kind of follow the path that's shown by the currents. So it's going to look something like this. We'll have a little more practice with this later to get this kind of exact, but if we know at the point -1, 1, we know the slope at that point, and we know that it's going to be sort of drift in the current according to this. It looks something like this. This is not very precise, but it's a general sense of the solution curve at that point. What about at 3, -1? So at 3, -1, we can go straight there, 3, -1. We know that that is the slope. The slope of the curve at that point is shown by that little tangent line. So we know that the curve must follow this trajectory, a very different trajectory. Sort of, there must be some sort of eddy or something that's forcing it to almost turn back on itself. And let's have a look at one more. So at 2, 3, at 2, 3, it's here. This is a very interesting trajectory. If we drop something in the river at that point, it is constrained to follow this line. It's just going to move in a straight line. And that, I think we even know the equation of that line. So for this one here, it seems like the equation of that line is y equals x plus 1. So we actually have, through the slope field, achieved one function that satisfies this differential equation. Let's just do a check. Let's see if dy by dx actually equals y minus x. So dy by dx, if this is the function, will be 1. And y minus x, so let's do that separately. Y minus x, well, y is x plus 1. X plus 1 minus x will just give us 1. And yes, these two match, and therefore y equals x plus 1 is a solution to the differential equation. So what you should get from this is that a solution curve to a differential equation will vary according to the point it is constrained to pass through. So before we begin practicing sketching slope fields, it's good to keep an eye out for 4 key segments that you'll be drawing a lot of. Okay, so the first is if the slope of dy by dx, if dy by dx is positive, so that means the slope of the curve at that point is positive, when you would get something that looks like that. Perhaps this dy by dx comes out to be negative, you'd get a segment like that. If dy by dx equals 0, we are looking at a horizontal segment. And if dy by dx is undefined, it is possible that the tangent line to the solution curve at that point is vertical. It's also possible that the function is just has a discontinuity there. So Desmos does not graph vertical tangent lines, but I tend to put them in just to kind of keep track of where the function is not allowed to go. And now, just to be a bit more specific, this positive slope, say that's a positive slope of 1, you may be asked to graph a positive slope of 2, so you just try and make it a little steeper. You're not going to be too specific about it. Or a tangent line, say a positive 1/2, would look like that. Similarly, if this is -1, then and you have a slope of -2, you'll make it a little steeper. If you have a slope of -1/2, you'll make it a little less steep. There's only so precise you can get with 1/2 or 1/3 or 1/4, but that's the general idea. So let's get into our first practice problem. We're going to sketch a slope field for the differential equation dy by dx equals x over y at the point shown. Maybe we won't sketch every single segment, as that will take a lot of time, but enough for you to get the general idea of how to approach these problems. So the first thing that's good to do is always to start by finding where the horizontal line segments are. So dy by dx will equal 0 whenever the numerator is equal to 0, i.e. whenever x is equal to 0, which is along the y-axis. So we can go and put in some horizontal tangent lines right there. Now I am skipping the origin, because 0 over 0 is indeterminate, so I don't even know what is going on exactly here, so I'm steering away from that. The next thing is to consider where dy by dx is undefined, and that's going to happen whenever the denominator is equal to 0. So when y equals 0, which is along the x-axis, I will put vertical line segments there just to know sort of places where this function can't go. And then we want to work on the points that are in the quadrants themselves. So have a little system for approaching these, and that's to fix a value of x. So let's say when x is 2. Fix a value of x and vary the values of y. So we're kind of looking at this column right here, and we're going to find the value of dy by dx for each point. So x over y here would be 2 over 2 would equal 1. That means we have a diagonal line segment of +1 there. This would be 2 over 1 equals 2, so we have a slightly steeper segment there. This we know is undefined. 2 over, 2 over -1 would be -2, so we have a negative segment right there. And this would be 2 over -2, which would equal -1. So we have more of a diagonal line segment there. So we are going to repeat. So it's going to take a little bit of time. We're going to repeat this now with x equals 1. And you could be working on that right now before I begin. So if x equals 1, then dy by dx in this case is going to be 1/2. So at the point 1, 2, the slope is a more gradual slope of 1/2. Here it would be 1 over 1, which equals 1. So here we have a perfect diagonal there. This we know is undefined. This would be 1 over -1. So we have some symmetry going on here for sure. So this would be a slope of -1. And finally, we would have 1 over -2, a gradual slope of -1/2. So we'll stop there and let Desmos do the work to finish creating this slope field. So here is a more complete rendition of the slope field, beautifully executed by Desmos. And we are going to practice a second skill related to slope fields, which is sketching solution curves. We did this on the first slide, but now we're going to practice it more carefully. So we'll start with the point 1, 2. So 1, 2 is here. And we know that the segment line here, the slope of that line, is the slope of the tangent line to the solution curve at that point. So we know for sure it's passing through there. And then we can only guess that it's kind of, the way to do this now is to just to steer between the line segments. Remember, imagine this is kind of the way the water is flowing in a river, and you drop that into the river, and it's got to follow the current. We know that along the y-axis, we know that the derivative is always 0, so we know it's going to kind of bank back up like that, and then by the symmetry we can connect it, and there we have a solution curve. And you may accidentally cross some of the other line segments, not the end of the world, but this is generally the rule of thumb, is to try and sort of guide it between the other existing line segments. So let's look at the point -3, 1. -3, 1 is here. And again, it seems to be following like that. Now, what you have to be careful with, though, is it's not going to be like the black solution curve on its side, because it wouldn't be a function then. And the differential equations really describe functions. So you would have to actually stop it there. We do know that at this point here, wherever that might be, we know that the y-coordinate is 0, and so the dy by dx is undefined. So we probably have like a vertical tangent line right there at this point here, but that would be the solution curve through the point -3, 1. And finally, let's look at 3, -3. So 3, -3 is, let's see, 3, -3 is here. And well, that, if you just follow that path, it is a straight line. We have to like avoid that, the origin, because we know dy by dx is indeterminate there. So the solution curve would look like this. In fact, it looks like the equation of that curve is y equals -x. So just to be sure that it works, let's just try seeing if it satisfies the equation of the differential equation above. So dy by dx would be -1. So that takes care of the left side of this. And then x over y would be x over, well, y is just -x, which would be -1. And so yes, they match. And this is y equals -x is one of the functions that satisfies this differential equation. So let's do another practice problem, sketching the beginnings of the slope field for the differential equation, shown in yellow, and we'll start it, and then we'll let Desmos do the rest for us. But let's begin by looking for horizontal line segments where dy by dx is equal to 0, and that's clearly going to happen either when x is 0 or where y minus 1 is equal to 0. So when x is 0 or y equals 1, we'll have a horizontal line segment. So we have one there, 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 all along the y-axis, and wherever y equals 1, regardless of the value of x. The next thing to think about is where is dy by dx undefined, and since neither x nor y are in the denominator of this differential equation, that doesn't happen anywhere. And now let's bring up our values and let's fix a value of x. Let's fix -2 this time. Start from the other direction. So I'll do the first calculation, and then afterwards I'll just write the results down. So this would be a half of x, which is -2, times y minus 1, and that comes out to be -1. So at the point -2, 2, the slope would be -1. And if you calculate the rest of them, you will get this. We know the slope is 0 here. We already knew that. The slope here would be 1. Slope here is a little steeper, 2, and even steeper down here. The slope would be 3. Again, a little hard to distinguish between a slope of 2 and 3, but you get the general idea. And now I will erase these and we will repeat. So you could be doing this yourself for the point when x is -1 for that whole column of values. So we're going to do, let's make this x is -1 and repeat. So again, if you just plug these values, combination of values in, you get -1/2, 0, 1/2, 1, and then this one you might want to check a little carefully. So for the point -1, 2, you actually get 3/2. So confirm for yourself that you get that. So now -1, 2 is slope of -1/2. It looks like that, followed by slope of 0, a slope of +1/2 here, slope of +1 there, and a slope of 3/2. Well, that's kind of hard to draw, but I'll do something a little steeper than 1. And that's how you start the slope field. And now we'll continue on to the next slide with a nice graph by Desmos. So just to correct the record, I did misspeak in the previous slide, and I said that the slope was 3/2. I'm showing you down here. I said it was at the point -1, 2, but it's at -1, -2. So just to correct that. And now we're going to practice sketching solution curves again. And let's start with the point -3, 3. So -3, 3 is here. And we know that we have to kind of guide our solution curve through the other segments. And we are not allowed to cross this horizontal segment here. These segments is kind of like a boundary, but we do know that eventually when it crosses the y-axis, this curve, it's the horizontal, the tangent line there is going to have to be horizontal. So let's aim to get through there. And then let's use the symmetry of the curve to say, well, it's probably going to go up and be perfectly symmetric on the other side. So that's that solution curve. And now what about through 0, -2? 0, -2 is here. And we see that the trajectories seem to be upside down. And again, let's stay between the segments. And we have something like that. It looks like a parabola, but might not be. And finally, 2, 1. 2, 1 is this point here, and that's where the dy by dx is 0, so the trajectory is not moving from that line. So we are pretty sure that y equals 1 is a function that actually satisfies the differential equation above, and you could plug it in to check. So we'll end with one last practice problem where you're given a slope field and you have to select the differential equation that matches it. And notice that something is going on at x equals -2. It's likely, because Desmos didn't graph it, but it's likely that we have vertical line segments there So I'm going to put them in just to give us an idea. There's a problem there. dy by dx is undefined there. So dy by dx is undefined when, let's see, dy by dx equals dne when x equals -2. So that suggests that we have to have x plus 2 in the denominator to make it undefined. So that immediately rules out this because x plus 2 is in the numerator there. Now let's look at where dy by dx equals 0. That seems to happen all along here where y equals 1. So we need y minus 1 in the numerator, but all three of them satisfy that condition. So let's look at something else. Notice that all the dy by dx segments, which are indeed tangent lines, they all have a positive slope. Well, if we look at the second one here, this dy by dx formula, or this differential equation, whenever y is less than 1, this will come out to be negative. So since there are no segments with negative slope, we'll rule this out, and we're left with the final 2. So when you get to this point, it's sometimes good just to pick a segment and pick a point and just go with it. So let's look. I usually pick a segment that looks like it has a slope of 1. So that point there, which is 1, 4, seems to have a slope that looks around 1. So if I put, let's see, if I put 4 in there and I put 1 in for x, I would get 3 squared over 3 squared, which is indeed 1. And now just to double check that is not the one below, I would have got, if I put it in the one below, I would have got 3 squared over 3 to the 4th, which would have been a much less steep line. So we know it's not that. So this is the correct differential equation. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.